For a 400 amp 240 volt single phase underground service, 4/0 copper is recommended. This provides the necessary ampacity and ensures proper voltage drop. Parallel 2/0 copper is not typically used for services over 200 amps. However, if the load analysis supports it, it may be possible but requires more calculations. A single 3-inch polyvinyl chloride conduit is sufficient for either option. Multiple conductors can be run in the same conduit for parallel installations, but ensure proper spacing and dirting. For service gear greater than 200 amps single phase, consult with a qualified electrician or the utility provider for specific requirements and equipment selection. Always confirm the actual load requirements of the house to ensure the proper service size. Contact the local utility to verify their specific requirements for a 400 amp service. Install multiple ground rods in accordance with local codes and industry best practices. Consider sleeving the conductors to protect them during installation and for future maintenance. Clearly label the conductors and equipment for easy identification and safety. When determining the appropriate conductor size for an electrical service, it's essential to adhere to the National Electrical Code, or NEC. The NEC provides guidelines and regulations for safe and reliable electrical installations. Article 310 covers conductors for general wiring, and it includes tables that specify the allowable ampacities of insulated conductors based on their size, insulation type, and temperature rating. For a 400 amp service, you need to select conductors that can handle at least 400 amps continuously. The ampacity of a conductor is the maximum current, in amps, that it can carry continuously under specific conditions of use without exceeding its temperature rating. Using Table 310.16 of the NEC, find the ampacity of 4/0 copper conductors with a 75 degrees Celsius insulation rating. The NEC typically allows you to use the 75 degrees Celsius column for terminations rated for that temperature, which is common. If 4/0 copper conductors with a 75 degrees Celsius insulation are rated for 230 amps each, one set of these conductors would not be sufficient for a 400 amp service. This is where parallel conductors come into play, or using a larger conductor such as the aforementioned 4/0. Parallel conductors involve using two or more smaller conductors connected together at both ends to form a single equivalent conductor. This increases the overall ampacity of the circuit. When using parallel conductors, the NEC requires that they be the same length, conductor material, insulation type, termination method, and have the same circular mill area. This ensures that the current is evenly distributed among the conductors. To determine if parallel 2/0 copper conductors are suitable, you would need to calculate the combined ampacity of two 2/0 copper conductors in parallel and compare it to the required 400 amps. Referring to Table 310.16, a 2/0 copper conductor with a 75 degrees Celsius insulation is typically rated for around 175 amps. Two of these in parallel would provide a combined ampacity of 350 amps, which is still less than the required 400 amps. Therefore, parallel 2/0 copper conductors would not be sufficient without adjusting for ambient temperature or other factors that permit higher ampacity. Keep in mind that these ampacity values are based on specific conditions, such as an ambient temperature of 30 degrees Celsius and no more than 3 current-carrying conductors in a raceway. If the actual conditions are different, you may need to apply correction factors or dilating factors as specified in the NEC. Conduit fill refers to the percentage of the interior cross-sectional area of a conduit that is occupied by conductors. The NEC specifies maximum conduit fill percentages to prevent overheating and ensure that conductors can be easily pulled into the conduit. Chapter 9, Table 1 of the NEC provides the maximum percentage of conduit fill allowed for different types of conduits and conductor combinations. For 3 or more conductors in a conduit, the maximum fill percentage is typically 40%. To determine if a 3-inch polyvinyl chloride conduit is sufficient, you need to calculate the total cross-sectional area of the conductors and compare it to the usable cross-sectional area of the conduit. The cross-sectional area of a conductor can be found in Chapter 9, Table 5 of the NEC. For example, a 4/0 copper conductor has a cross-sectional area of approximately 0.3224 square inches. If you are using 3/4/0 copper conductors for the service, the total cross-sectional area of the conductors would be 3 multiplied by 0.3224, which equals 0.9672 square inches. A 3-inch polyvinyl chloride conduit has an internal area of approximately 8.5 square inches according to Chapter 9, Table 4 of the NEC. Using the 40% fill limitation, the maximum allowable fill area in the conduit would be 0.40 multiplied by 8.5, which equals 3.22 square inches. Since the total cross-sectional area of the conductors, 0.9672 square inches, is less than the maximum allowable fill area of 3.22 square inches, a 3-inch polyvinyl chloride conduit would be sufficient for 3/4/0 copper conductors. If you were considering using parallel conductors, you would need to calculate the total cross-sectional area of all the parallel conductors and compare it to the conduit fill limits. For example, if you were using 6/2/0 copper conductors, 2 sets of 3 parallel conductors, the total cross-sectional area of the conductors would be 6 multiplied by the cross-sectional area of a 2/0 copper conductor, which is approximately 0.2043 square inches. This equals 1.2258 square inches, and again is well within the limits. Dating is the reduction of the ampacity of a conductor due to factors such as high ambient temperature or the presence of multiple current-carrying conductors in a raceway. The NEC requires that conductors be derated under certain conditions to prevent overheating and ensure safe operation. If the ambient temperature is higher than 30 degrees Celsius, you may need to apply a temperature correction factor to the ampacity of the conductors. The temperature correction factors are found in Table 310.16 of the NEC. For example, if the ambient temperature is 40 degrees Celsius and the conductor has a 75 degrees Celsius insulation rating, you would multiply the ampacity of the conductor by a correction factor of 0.88. This would reduce the ampacity of a 4/0 copper conductor from 230 amps to 202.4 amps. When there are more than 3 current-carrying conductors in a raceway, you may need to apply a derating factor to the ampacity of the conductors. The derating factors are found in Table 310.15 current of the NEC. For example, if there are 4 to 6 current-carrying conductors in a raceway, you would multiply the ampacity of the conductors by a derating factor of 0.80. This would reduce the ampacity of a 4/0 copper conductor from 230 amps to 184 amps. When using parallel conductors, each set of parallel conductors is considered a single conductor for the purpose of applying derating factors. Grounding is the connection of electrical equipment and systems to the earth for the purpose of providing a low impedance path for fault current. A grounding system is essential for electrical safety, as it helps to prevent electric shock and reduce the risk of fire. The NEC specifies the requirements for grounding electrical systems in Article 250. A ground rod is a metal rod that is driven into the earth to provide a connection to ground. The NEC requires that all electrical services have a grounding electrode system, which typically includes 1 or more ground rods. The NEC specifies the size and type of grounding electrode conductors that must be used to connect the grounding electrode system to the service equipment. The grounding electrode conductor must be sized according to Table 250.6c6 of the NEC, based on the size of the service entrance conductors. The NEC also specifies the requirements for bonding, which is the connection of metal parts of electrical equipment and systems to create a low impedance path for fault current. Bonding helps to ensure that all metal parts are at the same electrical potential, which reduces the risk of electric shock. Sleeving is the process of enclosing electrical conductors in a protective covering, such as a plastic or metal sleeve. Sleeving can help to protect conductors from physical damage, moisture, and other environmental factors. The NEC does not specifically require sleeving in all situations, but it may be required by local codes or utility regulations. Sleeving is often used in underground installations to protect conductors from abrasion and corrosion. Labeling is the process of marking electrical equipment and systems with information about their function, voltage, current, and other important characteristics. Proper labeling is essential for electrical safety, as it helps to prevent confusion and errors during installation, maintenance, and troubleshooting. The NEC requires that all electrical equipment be labeled in accordance with Article 110.21. Labels must be durable and clearly visible, and they must provide sufficient information to identify the equipment and its function. For example, service equipment must be labeled with the service voltage, current rating, and the location of the main disconnect. Conductors must be labeled to indicate their function, such as phase conductors, neutral conductors, and grounding conductors. In summary, selecting the appropriate conductor size for a 400 amp underground service requires careful consideration of the NEC requirements for ampacity, conduit fill, dirting, grounding, sleeving, and labeling. Consulting with a qualified electrician or electrical engineer is recommended to ensure that the installation meets all applicable codes and regulations and provides a safe and reliable electrical system. Always refer to the latest edition of the NEC and any applicable local codes and regulations for the most up-to-date information. It is also recommended to have a load calculation completed by a qualified professional to ensure the service is sized appropriately for the expected load. This calculation will take into account all of the electrical loads in the house, including lighting, appliances, and heating and cooling equipment. The load calculation will help to determine the minimum size of the service entrance conductors and the service equipment. If the load calculation indicates that the actual load is less than 400 amps, it may be possible to use a smaller service. However, it is generally a good idea to oversize the service slightly to allow for future expansion. The utility company may also have specific requirements for the size of the service entrance conductors and the service equipment. It is important to contact the utility company before starting any electrical work to ensure that the installation meets their requirements. When installing the service entrance conductors, it is important to follow all of the manufacturer's instructions and the NEC requirements. The conductors must be properly supported and protected from physical damage. The conductors must also be properly terminated at the service equipment and at the meter. When installing the grounding electrode system, it is important to follow all of the NEC requirements. The grounding electrode system must be properly connected to the service equipment and to the earth. The grounding electrode system must also be properly tested to ensure that it is effective. The installation should be inspected by a qualified electrical inspector to ensure that it meets all applicable codes and regulations. The electrical inspector will verify that the installation is safe and that it meets all of the NEC requirements.